Okay, let's, tertiary structure, which one's that?
That gives it function.
Okay, so the tertiary is responsible for function. What else? How is it formed?
It's on the amino acids. Not the backbone, but
The secondary structures
Yeah.
are folded in and interacting with them.
Don't say secondary, because then that makes it sound like you're talking about the secondary structure of the protein, which is the backbone interacting backbone. But the tertiary structure isn't backbone. What's interacting with what?
the functional groups.
The R groups, the functional groups. Okay. So it would be something like an alanine interacting with an alanine. Why would those two guys interact with each other?
They're the same.
They're both branch chained, so they're nonpolar. So if I've got a protein chain and there's a side chain here and a side chain here, both of those, what's going to happen with that molecule, that chain? So since this is nonpolar and this is nonpolar, those things would be attracted to each other. So we'd end up with something like this. And that interaction between the two of them, what do we call this when they interact with each other in a tertiary structure? It's folding. The protein folds, and when it folds, then it's in its tertiary structure. So it gives its function, so when it loses its function, what's the name for that?
Nature.
Denatured. So when we denature, it's that breaking. That interaction between the side chains in the tertiary structure, when that unfolds, when those guys let go of each other, then that protein no longer has its function. Okay, and the quaternary structure?
Multiple proteins in there, tertiary structure.
Tertiary structures, multiple individual tertiary structures. So these are completely separate proteins. They're not chemically connected to each other. So I've got a chain and it folds into its tertiary structure, and I have a different chain and it folds into its tertiary structure, and those two tertiary structures come together to make a quaternary structure. So not all proteins have quaternary structures, but if you have a protein and it's got a quaternary structure, then that's what gives it function. Can you give me an example of something that's got a quaternary structure?
Hemoglobin.
Okay, how about a comparison between competitive and non-competitive?
Competitive inhibitors bind to the active site, non-competitive to the smart site, the active site.
And is there a way to overcome competitive inhibition?
Yeah, adding more substrate.
Best example of that situation would be kid, animal, drinking ethylene glycol, antifreeze, and then getting them drunk to make sure that the side chain doesn't, the liver doesn't create a toxin.
Is that how you spell substrate? No.
Probably not.
Okay.
It's probably that.
The diagram there, yeah.
Oh yeah, it's right there. There you go. And what about the non-competitive.
They find other areas changing the shape of the active site.
So if an enzyme is interacting with a non-competitive inhibitor, it's kind of broken. There isn't like a way that we can change that unless we remove the non-competitive inhibitor. So lead poisoning, if you could get rid of the lead, then it would stop interacting with the protein. So you'd want to give the person some kind of organic molecule that chelates for lead. Other than that, the person is going to be showing some sort of disease associated with that enzyme not doing its function because it's broken. All right, so we're going to add trypsin to this. Where does trypsin cleave?
After the K's and after the R's.
And it's after the K.
Is it always gonna be on the C side,
Yes.
no matter what the enzyme is, it's always gonna be on the C side?
Oh, no.
Just for this.
It's for this enzyme, it's always on the C side terminus. Did I miss any? Are we okay with how I drew it on one side and then swapped it to the other side when it flipped around? Okay. So you've effectively broken this protein up into a bunch of smaller chunks, which the smaller chunks are going to be a lot easier to digest. This is one of the reasons like a bird will eat its food and then regurgitate it to give it back to the baby birds. They can't digest proteins as well. Okay, so what's going on with this diagram on the left?
The enzymes are right side?
So we've reached the maximum turnover rate of this enzyme. I throw substrate in. Initially, it can handle all the substrate, you get it, and so the reaction happens at a certain speed. But eventually, I throw so much substrate in there that the enzyme's working as fast as it possibly can. So at that point right there, the enzyme's doing as much as it possibly can, and throwing more substrate in is not going to increase its speed. Every time it finishes one reaction, it turns around and it sees another substrate right there ready to go, and it reacts on it. And so the other one, what about this this second drawing here?
Adding enzyme to it.
You just-
Increasing enzyme, increasing substrate.
Yeah, so if I just keep throwing enzymes in, it doesn't matter. The thing can go as fast as I want it to. If I throw a gajillion enzymes in there, the reaction's going to happen really, really fast. So, the enzymes are just not fully occupied. I have plenty of enzymes to do all of the reacting with all of the available substrate. So if I need a reaction to happen real fast, I can just throw in a lot more enzymes. If we think about enzymes being tools or workers, if you, I mean, how long does it take to build a house? Like 6 months, 3 months, you know, whatever. How long does it take on those reality TV shows?
3 days.
Like 72 hours, and you go from nothing to like a full-fledged house in 72 hours. So that's the situation. We throw up as many workers as we possibly can, and all the workers are always doing all the work all the time, and so the job gets done really quickly.